Hello everyone, thank you for attending my talk and thanks the organizer for giving me this opportunity. So I'm Arjun, a PhD student at PSI and EPFL, and I've done this work with my collaborator Loic from Grenoble and my advisor Andreas Schleukli from EPFL. So I will try to, in this talk, I'll try to give a general method to study Wilson-Fisher criticalities, in general ON Wilson-Fisher criticalities, using truncated quantum rotors. And then in particular, I will show you some results for the O3 conformal field theory using this kind of models. So to start, I will briefly remind you about quantum rotor model, then show the mapping of these quantum rotors, truncated quantum rotors, to spin models in case of O2 and O3 rotors. Then I will show you how to put the rotors on the fuzzy sphere and determine the critical point and the speed of light. And then finally, I will show the emergence of the O3 conformal field theory. So the rotors, you can think like for a O1 rotor is just a spin going up or down. A O2 rotor is something that can go on a sphere, on a circle. O3 will be something that can point on the surface of a sphere. O4 would be on some hypersphere and so on. So the Hamiltonian is just L square, the angular momentum square operator. And now when you have many such rotors, the kinetic term is this L square, and you have an interacting term that wants to align the rotors. So these n are just position operators of these rotors, and this is a ferromagnetic interaction. So it wants to align nearest neighboring rotors. So now if you plot if you want to see the phase diagram with respect to this coupling, if you have a very little coupling, you will be in a paramagnetic phase, and then if you turn on the coupling high enough, then you will go to a ferromagnetic phase because the rotors will try to align. And in the middle, you get a ON Wilson-Fisher criticality. And since we want to study this model numerically, first thing we are concerned about is the Hilbert space of this. So for one rotor, the Hilbert space is just up or down, so it's a finite Hilbert space. But already at O2 rotor, you have an infinite Hilbert space, and you need to truncate it. And it turns out that if you truncate it at L equals to plus minus 1, so you're keeping only 3 states, you still get O2 Wilson-Fisher transition. And so this is the minimal truncation that you can do. If you do more than that, you get extra states, and less than that, you don't get the O2 transition. And then for O3, you have the spherical harmonics, that is for the kinetic part, the function of the kinetic part with Lm quantum numbers. And if you truncate it at L equals to 1, so you're keeping only S and P orbitals, you can already get O3 Wilson-Fisher transition. And so first, I will show you mapping of these truncated rotors with some known spin models to just say that those known spin models already have these O2 or O3 criticalities. So if they map, they should have the correct transition. So mapping to spin models. So for the O2 theory, we are truncating at -1, 0, and 1. So the kinetic part is simple enough, and then we compute the two-body matrix elements, so you get a 9 cross 9 matrix. And this model actually, this truncated rotor actually exactly maps with the spin 1 single ion anisotropic XY model, the model Andreas showed yesterday on the fuzzy sphere. So this term is the size is square is exactly the kinetic term, and this exactly the matrix elements are exactly the same. For the O3 case, we are truncating at S and P orbitals. So the kinetic part is 0 for S, and then you have P orbitals, and then we can again compute the two-body matrix elements. And it turns out that it has a close relation with the spin-half bilayer Heisenberg model. This model, you can think into 2 parts, the symmetric and antisymmetric in terms of the layer part. And the antisymmetric part exactly maps with the two-body matrix elements. So at the level of the matrix element, they are exactly the same. So at this point, I should make a comment that there has already been a study on the O3 Wilson-Fisher criticality on the sphere, but the crucial difference between our and their model is the filling fraction. So in this model, that is basically a variant of the bilayer model, where you have 2 layers and the spin indices. So you have kind of 4 local orbitals and 2 electrons in them. And in our case, we have 4 local orbitals and 1 electron. So we have a much minimal Hilbert space. And as a result, we don't have any intruder states. At least we don't see any. So with this, let me move on to how to put these truncated rotors on the fuzzy sphere. Now, so we have 4 flavors from the s and p orbitals. And now the Hamiltonian will look basically the same as the Ising Hamiltonian that we know of. The H0 part is the same as the Ising fuzzy sphere Hamiltonian, just with 4 flavors. And then the O3 has 2 parts, the interacting and the kinetic part, and that's the same table that I have shown below for the interacting and the kinetic part. Is like a transverse field between s and p orbitals. And then you put them on the fuzzy sphere, so each momentum orbital now gets 1 rotor, and yeah, so you have 1/4 filling. And this model has some symmetries. The SO3L is from the, of course, from the sphere rotation part. You get angular momentum multiplets from that, and then you have the internal symmetry O3I that divides into improper and proper parts. So this gives you the S multiplets, and this the Z2 part, that is basically how many electron you have on the p orbital, gives you the Z2 part. And we get quantum numbers corresponding to that, and then we use all these quantum numbers to do the ED in specific sectors. So we managed to reach until 12 electrons in 48 orbitals using ED, and then
doing SO3 quantum number, or just you want something different? Global situation.
So of course we use the SZ for so 12 electrons in 48 orbitals for ED, and currently we are at 28 electrons in 112 orbitals for DMRG. It's still running. And once we have, now we set it up, and then we try to determine the critical point, and then we use the formalism of the conformal perturbation theory as described yesterday. So basically, near the critical point, you are describing your system as some perturbation over the CFT, and this perturbation has to be some coupling with a CFT operator and symmetry constraints. And it turns out that there is only one relevant operator that is allowed in this formalism, at least in our case, unless you are at a multi-critical point. So your state operator correspondence gets somewhat modified with this extra term. So G epsilon is your coupling, and this is the diagonal OP coefficient with epsilon with the level you are considering. So now you have 2 free parameters, C and G epsilon. So you need 2 levels to fit them. So we use the sigma and the first descendant of sigma to fit C and G epsilon. Those are the lowest levels basically. And once you fit it, you get something like this as a function of H, and where this G epsilon becomes 0, you restore back your conformal symmetry, and then hence you are at the critical point, and then you get it as a function. I mean, with system size, the critical point converges, but of course there is some drift for smaller systems. And then we go at the conformal point, at the critical point, and try to see what emerges, and we can more or less clearly see the emergent conformal symmetry. So these are the indices. So this is S is the internal symmetry, as I told, and plus corresponds from the Z2 plus or minus. Let me explain some of the legends here. So different colors in the marker correspond to different system sizes. Up to 12 is ED data, and after that is DMRG data. And I put some of the reference levels. So this green dashed line is primaries that are known from Bootstrap, and red dash means descendants of those primaries, and solid green line means exact levels, like there are only 2, T mu nu and the conserved current, and red solid are the descendants. And with that you can see, so this is the sector where you have the ground state is shifted and scaled using the C that I have fitted before. And then you can see the epsilon is converging, and then its descendants are also fairly convergent. And T mu nu, is conserved, so you don't have any descendants on the other side, and you see epsilon prime and other expected operators.
So
or unexpected.
Huh?
Or also unexpected operators.
Yeah, there are some other unexpected operators, of course.
Why, of course? Surprising.
So the data was computed at the critical edge you get from the extrapolation, or
so for each system size, the critical edge is slightly shifted. So the data is, so for system size 4, the critical point, let's say 16, but system size 28, it will maybe 15.5. So it's slightly shifted.
So then for each size you use that edge.
Exactly. And then you can look at some other sectors. So these are the sigmas. So these two I blurred because these are the levels we are using for the fitting. So these are always exact. And then you can see some of the descendants. And I think these are the levels that are predicted using epsilon expansion already. And the values are not so accurate, but yeah, they are. We see them. And then you can see this sector S1 plus where there is the conserved current. So there is no descendants on the left-hand side and descendants on the right-hand side, and so on. There are other new operators, phi mu prime. And here in this sector, this is a bootstrap level, known level, so you can see new level. And perhaps this is one level that I find a bit surprising, this level. It seems to be saturating the unitarity bound, and it's not moving much. And then I also don't see any descendants on the side. I mean, I'm not sure whether this is a descendant of the T or T mu nu prime. So this is something we need to figure out, perhaps using conformal generators. Whether
that one is slightly broken Heising type, right?
Yes, it's like C mu nu rho sigma kind of level, right? C4 kind of level, but I'm not sure. I mean, I don't see any descendant here of that. So yeah, so yeah, it may be broken and not conserved, but then it will have descendants. So there's something to be figured out, I guess.
This W is the power of the leading irrelevant operator?
Yes, exactly.
Remind me what it is?
Huh?
What is it?
0.76 or 77.
T2.
And this is, okay, I didn't mention that the rightmost is the smallest system size and leftmost is the highest system size. Then we also compare our results with some of the large charge prediction. So large charge basically is telling you, so LC even is your large charge for S plus sectors and LC odd large charge for S minus sectors. And you see, and these are our data, fuzzy sphere data. So up to 4 it matches quite well, and then it starts to deviate, or perhaps also because in these higher charges we don't have very high system size. We have until 10. And these are some phonon primaries that large charge predicts. So here, the first one you see very well, there is the phonon primary, but afterwards we first need to probably distinguish between primaries and descendants to conclusively tell whether these levels are present. But we already verified the lowest ones and some of the phonon primaries.
Can you remind me what is the expected scaling behavior in the large charge? Asymptotic behavior of the scaling analysis.
Q to the power minus half or plus half. Yeah, I don't remember. So there are this Wilson coefficient that you need to fix. I think Q to the power minus half, Q to the power plus half, and 3 half, and then you fit the Wilson coefficients to that using bootstrap data.
And what size is this figure?
Which one?
The upper figure.
This is 10. This too is 10, but then these are 26. This is, I think, 14. For the lower, we have done the MRG for these levels mostly. And then perhaps the most interesting sector is this S0 minus, where we see this Lorentz pseudovector or 3 pseudoscalar primary. So I call pseudovector because it's also parity, space-time parity odd. And this particular level seemed to have an important role in dimerised Heisenberg antiferromagnets. So these are these two different couplings. So
sorry, and about this scanner, S is charge, right?
S is charge.
So in the
S is the O3 charge. Yes.
So in the previous one, if you didn't compare the large charge predictions on this plot, the previous one.
Well, for 0 you cannot compare large
charge.
charge.
Plot where you looked at the lowest state as a function of S on the previous plot. Not this one, the one before.
This one.
Yeah.
This is S2 plus. This is S2 plus. I compare only one sector here. I show.
What about the top plot where you?
The top plot is the lowest level in each S sector.
Yeah, exactly. So there's a large charge prediction for that. Did you?
Yeah, but for 0 there is no large charge prediction. 0.
But you also have all the way 1 up to 7. Can't you? So you can compare it.
I can compare, but not for 0. S equals to 0. You don't
agree, but you have much more than 0. You have S from.
Yeah, but this is my comparisons.
Oh,
those are the comparisons. Yeah, those are the comparisons.
Oh, okay. Sorry.
Okay, so.
Sorry, can you fly back, please? Right here. So you have S mu and you have epsilon mu nu. S mu. What, is there a derivative there?
No, this is not the derivative. This is this antisymmetric tensor. For non-scalar operators, you have descendants also. Just above it, it's not derivative. Sorry, there is a derivative. Sorry, I didn't write. There is a derivative, but then you contract it. So is it the same?
So S mu is the primary.
Yeah, the S mu is the primary. Sorry, I should have put it a name. Yeah.
So it should be epsilon partial S.
Yes. Yes. Yeah. Sorry, didn't notice that. So. In this class of models, so blue is J prime and red is J. And in this dimerised antiferromagnets, Heisenberg antiferromagnets, there are two different phases. One is the columnar phase and the staggered phase. And then there was a paper in 2008 where they find that in the staggered phase, there are vastly different critical exponents that don't match with the Heisenberg universality. And they thought perhaps there is a new Heisenberg universality. And after following that paper, there have been many papers, and I put some of them here. So then people thought that this perhaps comes from some sort of cubic interaction that is allowed in the staggered model and not in the columnar model. And they find the scaling dimension to be somewhere between 3.2 and 5, but yeah, they also mention that it may even be relevant. So they are not sure. And then there have been other papers where they find this to be 3.57, 4.25, 4.4, and so on. So we also confirm that this indeed is a relevant operator. So already it's above 3. So it should be relevant. So there should not be any new universality class from there. And in this case, we have data up to 22 electrons, and we get around 3.3. And you can see that it didn't converge yet. So it's very far from converging. We need higher system sizes. Since this level seem to have a bit of quite high entropy, so it's very hard to do the DMRG for higher system sizes. And double or single power law, both extrapolation gives around 3.8. That somewhat matches with what the 5-loop expansion people are doing. It's unpublished, that's around 3.72. Somewhat matches. And then we check the free O3 theory. And in this sector, S0 minus, so the same sector, you have a primary for L1 that's around 3.5. So we are quite sure that this is the origin of this level in the free theory is the origin of the S mu in our interacting theory. And this actually looks like a topological theta term, as they also mention in this paper. So perhaps this has some more importance. Even though it's irrelevant in the bulk, I don't know what happens. What effect does it have in the boundary? So this is something to keep in mind. And these are all the scaling dimension data. We have also computed some OPE data. So it became too dark. So this was the first order conformal perturbation theory. And if you just invert this equation and take the derivative of the gap with respect to the coupling at the critical point, you basically get the OPE coefficient, and then you can, here we have result only until 10 electrons. You can see, so these are bootstrap, the green with primaries, and these are bootstrap with, I mean, not bootstrap, but these are with descendants, so known levels. And then you can see them, they are converging. Some of them takes a bit longer to converge because of the same reason Andreas mentioned yesterday, that there is level repulsion between these two, so the wave function content is exchanged, and so on. And then we have OP results for all other sectors. I mean, some of them have comparisons, so we can see that they are converging well. So these T levels are incredible. They are converged always, basically. And then some new OP coefficient. So we have all the OP coefficient with all levels with epsilon. And with that, let me summarize and give a brief outlook. So we give a minimal model for studying ON CFTs via rotors. So any n, it should be possible. In particular, I show you the results for scaling dimensions of O3. There are some lingering questions. So is there a new conserved quantity? Probably no, probably yes, I don't know. It may be just weakly broken. We also give some new insights on the dimerised antiferromagnets. Perhaps there is some relation with the theta term. And also confirm some prediction from the large charge. Generalizing it to O4, O5 should be straightforward. For O4, you have hyperspherical harmonics. So you have 3 quantum numbers, K, L, M. And if you just truncate it at K equals to 0 and 1, you have 5 orbitals, 1 electron per 5 orbitals. So, and I guess O5, O6 would be very similar. So we should be able to generalize up to probably quite high n. And then we also show some OPs with a relevant coupling, and perhaps we can also compute some OPs with relevant coupling. So we have some preliminary results for that. With that, thank you for.
All right, questions?
Just wondering, do you have any plan on studying other interacting scalar theories? For example, cubic for 3 scalars and 4 scalars, things like that?
No, not currently, no.
You said that you truncate to L equals 1. Is there any benefit to do higher L's?
But I think then the Hilbert space is not minimal. And the fear is that then you will have excitation. There are not necessarily CFT excitation. And if they infiltrate the low energy part, they can also hybridize. And then you will probably not get just the CFT and some other garbage states. We want to keep it as minimal as possible.
This pseudovector that, okay, you say it's not relevant, but it's quite close to marginality, so it can affect physics. And with your methods, probably you can extract some OPE coefficients and so on, which will tell you how exactly it affects. If that operator is present in the effective action with a small coefficient, then it's going to modify the values of effective critical exponents. So yeah, perhaps you can shed light on those experiments, even if it was not an exact new universality class, but it was just a correction to scaling, which was anomalously large. I think you can shed some light on those experiments.
Yeah, definitely. But those are all just correction to observables and critical exponents. But I was thinking that, but it don't give rise to any new phase. So perhaps in the boundary it can have even more interesting effect and give rise to new phase. That I don't know. I asked the audience for that.
No, but you said there were some experiments which saw something weird.
It's Monte Carlo.
Oh, Monte Carlo. Okay, so they saw weird things. Now you can explain why they saw weird things. Because there was this operator in the effective action. It was decaying to 0, but very slowly, and it was affecting other things. That's the reasonable explanation, right?
Yeah, exactly. And now there are 2 operators that are affecting. So epsilon prime is affecting, and this operator is affecting. Those are very too close. Now, if you have only one operator that changes your observables and couplings, you can get only monotonic behavior. But if you have 2 operators, you can get non-monotonic behavior because the couplings can be opposite side signs. So.
But you said that the number is very close to 3.8, right?
Yeah, exactly. So these two are very similar, right? The epsilon prime is. Huh?
It would be impossible to see if it's 3.7, 3.8, it would be very close to distinguish that. You said it could be have an opposite sign, yes.
Right, right.
Which range of value you need to see really the change in the...
I see what you mean.
Yeah.
So actually in the paper, you know,
but this is spin 1, so I think we can probably just...
the answer is in the paper on the lower right there. It's around, 100. You need to go over 100 to see the non-monotonic behavior.
Yeah.
But it has spin less than that.
That is also another factor. That one has spin L0, the epsilon prime, and this is spin 1. So
I think this dimension is so close to 3 that you can assume that its coupling is basically constant and pretend that you say theoretically it's not a universal quantity. You can pretend that it is and compute changes in scaling dimensions, and that's going to give you should give you a very good description of these Monte Carlo simulations. I have a feeling.
Yeah.
In classical O3 model, there is this discussion whether it's, whether ON is broken by the cubic anisotropy.
Yes,
is this relevant here, or do you really have hard spin constraints?
Yeah, so we see that operator at S4 plus, but that operator will not have any coupling in our case because we are not breaking the O3 symmetry.
But you see that it is relevant or irrelevant?
It's currently, if you extrapolate, it goes to relevant, but in our studies, it's now it's 3.1.
Because that's also what the conformal bootstrap says.
Conformal bootstrap says 2.99, very close to irrelevant. Yeah.
But it's probably fair to say that our accuracy is not comparable to conformal bootstrap regarding that question.
Of course. Yeah. And we are at 3.12 currently with 28 electrons from that level. There was another question there.
Can you flash the Hamiltonian again, please?
For this?
No, just the one that you're simulating. So HTR.
So this is this one basically for the spin part. Then the Uij will give you this Haldane pseudopotential. This is only the spin part I write. The angular momentum part is
not written yet. It will be very similar to the.
Somehow, maybe there is a type of HTRI appears.
Yes. Should not be only this one is there. Yeah.
But basically, it's like you have a spin 0 channel, spin 1 channel, and spin 2 channel, and HTRI is like direct sum of those channel interactions.
So this will be this. So HTRI. So this, if you do the tensor product of 2 of this, so you have the 16, and then HTRI is a 16 cross 16 matrix.
16. This 4 components.
So how many pseudopotentials have you used?
V0, V1 is like the Ising, but just need to optimize the V0.
So in total, how many tuning parameters?
V0, and I mean we have another tuning parameter that we put here, VL. That we tune VL, and so this is kind of comparing this and this. So we tune actually 2 tuning parameter in that sense, tuning parameters for, and then actually we tune that tuning parameter and then extrapolate the value of epsilon. So
where is the best?
And could you compare what you observed? How does the numerics look better than the Heisenberg bilinear, or
the bilayer model? Yeah. The bilayer model. The thing is that in the paper there is extrapolations, right? I mean, the raw values look better, but of course it don't look better than the extrapolated values. But But there are also very few levels mentioned, so we cannot compare the amount of levels that we have.
All right. Well, I want to thank Arjun again.